So this last section within chapter 2 deals with one-to-one functions and their inverses. So the idea of the inverse is that the inverse of a function is a rule that acts on the output of the function and produces the corresponding input. All right. So kind of what we're saying here is, if I have a point x comma y, all right, we know that we could use a function. So f of x equals some function of x. Let's just say it's 2x plus 1, right? And what we could do is say, okay, well, if x equals 1, so if we want to evaluate f of 1, then f of 1 would equal 2 times 1 plus 1, or 3. An inverse says that if we start with 3, so I'm going to use a different notation. I'm going to use h of x, or better yet, h of 3. If I take this function that I'm looking for called h and I substitute in 3, I should get 1 as the output. So in a way, you can kind of think of this as like, if you have a function and you input x, you're going to get f of x. Then if you have a completely different function and you use f of x and you substitute it in, you should get the original x value out, okay? Now, not all functions have inverses. This is just a thing, and we need to be careful about that. But those that do are called one-to-one. So sometimes when we look at this and we say, okay, functions that are one-to-one, what does it exactly mean? All right, well, we're going to go over that in a second. But sometimes in order to find the inverse, we may have to restrict the domain, okay? Which we could say, listen, overall, this doesn't have an inverse. However, if we restrict the domain, it does have an inverse, okay? So real quick first, the definition of something that is one-to-one, all right? So a function with domain A is called one-to-one if no two elements of A have the same image. That is, f of x1 cannot equal f of x2 whenever x1 does not equal x2. Another way of writing this that I think makes a lot more sense is if f of x1 equals f of x2, then x1 has to equal x2. In other words, if you get the same exact output, you better have the same exact inputs as well. Okay? So an easy way to really demonstrate this would be to determine if a function is one-to-one, we use the horizontal line test. Okay? So if you think about this, okay, I'm just going to go ahead and draw just a quick function real quick. And what we're going to do is, I don't know, we'll draw something very simple. Let's say, oh, this is a good one. All right, so this is f of x equals x cubed, okay? Well, number one, we know it's a function because, well, first, I'm labeling it f of x. But we know this is a function because if I were to do the horizontal or the vertical line test, I would definitely get, one intersection at each vertical line I draw. But what we're interested in is this one-to-one. So all we have to do is just draw a horizontal line. Notice I hit the function once right there. I could try it down here. I still only hit it once. I can try it over here. I hit it once again. So we know, so f of x equals x to the third is 1-to-1, which means that f of x equals x cubed has an inverse. All right. Now we're going to learn how to find it, but right now we just want to be able to examine, does it have an inverse? Okay. So there is a really easy picture there. Now the next example I want to do is just using the actual definition. I think it's really important. So we're going to show that the function f of x equals 1/4 x minus 4 is 1 to 1. Okay? So what we're going to do is let's suppose that there are numbers, and we're going to call them x1 and x2. Oh, such that f of x1 equals f of x2. So that is literally just the definition copied down. I did nothing special there. Then what we're going to do is we're going to find f of x1 and f of x2. And what we need to show is that x1 equals x2. So we assume f of x1 equals f of x2 to be true. We will show that x1 equals x2. So let's go ahead. We're going to come directly underneath the f of x1 equals f of x2. And we're just going to substitute in our function. But instead of writing x, we're going to write x1 and x2 respectively. So we get 1/4 times x1 minus 4 equals 1/4 times x2 minus 4. Now, I just go ahead and do basic algebra. I will add 4 to both sides. That gives me 1/4 x1 equals 1/4 x2. And now if I just multiply both sides by 4, notice I get x1 equals x2, which is exactly what I needed to demonstrate. So literally, that's it. That's all you got to do. Personally, the easier of the two is by far the horizontal line test. So if I were you, I would just stick to the horizontal line test. Remember, you can easily just use Desmos to graph something real quick and just try to visualize a horizontal line, or type in horizontal lines and see how many times you touch the axis. Or I'm sorry, you touch the function, my bad. All right, so now we've arrived to the big definition of this section, which is the definition of an inverse function. So first, you got to let f be a one-to-one function, meaning one-to-one, we pass that horizontal line test. So if you pass the horizontal line test and you demonstrate that a function is one-to-one with domain A and range B, then its inverse function has a domain B and range A, which is defined by, now this is read, the inverse of f of y. So the inverse of f of y equals x if and only if f of x equals y for any y and b. So here's what this is saying, okay? Oh, that looks bad. Here we go. So say, for example, we have a couple points, all right? And I'm going to pick very common, easy ones. So we have -2, comma -2. We have -4, comma, let's say 8. And then we have -6, comma 7, I guess. All right, I'm just making these points up, okay? So the first thing I want to do is just demonstrate that even with these 3 points, we have something that's one-to-one. So what I'm going to do here is just go ahead and quickly graph them. And I'm not going to be really, really specific on this. I'm just going to go ahead and graph them in the quadrants that they should be. So we have -6, comma 7. So that's going to be like up here. And I'll just label it -6, comma 7. Then we have -4, 8, which is going to be up here. -4, 8. And then we're going to have -2, -2, which is going to be like all the way down here somewhere. Okay? Now, if I were just to connect the dots, this is what I would have. And then using our horizontal line test, here we hit twice, so we fail. So this does not have an inverse. Now, let's try this example, which does have an inverse. There we go. So we're going to pick the points 0, 2, 1, 4, and 2, 6. Okay? Now, if I plot these points, I get 0, 2, which is right here. 1, 4, which is like up here. And then 2, 6, which is all the way up here. Now, if I connect these dots and I do my horizontal line test, no matter where I hit it, I only hit once. So this is 1 to 1. And what that definition of an inverse says is that if we were to group our domain, which in this case will be 0, 1, and 2, and then we were to write the range, which is going to be 2, 4, and 6, we can map all of these x values to each one of these y values by using our function. The inverse says that what you're going to do is you're going to take your range and you can map them back to the original x value. Okay? And that is what we call the inverse of x. Okay? Now, what really makes this powerful is that when you go ahead and you graph something, you're going to see that you create something like mirror images. So let's go ahead and let's look at this example here, where we have the points 0, 2, 1, 4, and 2, 6. So I'm just going to erase this stuff right here. If I were to go ahead and just swap all the x and y positions, so I get 2, 0, 4, 1, and 6, 2. So notice I'm starting with the output and I'm trying to get back to the input. And I were to plot these, look what you get. You get 2, 0, which is right about here. Then you're getting 4, 1, which I would say is like right about here. And then you get 6, 2, which is right about here. And you get this line segment right here. And if I were to just superimpose in the green line, which is y equals x, notice you get mirror images of each other. Okay? Now, there's a really famous inverse function that really demonstrates what I'm talking about here. So if I were just to go to Desmos real quick, so I'm just going to go ahead and click over on Desmos real fast for us. All right. So first thing I'm going to do in green is I'm going to highlight y equals x. Okay. All right. And I'll make it a dashed line. Okay. Now, the two functions that I'm talking about that are inverses of each other are the functions f of x equals e to the x, and then f of x equals the natural log of x. And notice how you have mirror images of each other. In fact, I'm going to go ahead and just click on the x and y intercepts respectively, because you can see here at the y-intercept, this is 0, 1. And when you reverse the order, you get the inverse of e to the x, which is 1, 0, which we know to be the natural log of x. So therefore, whenever you have inverses and you graph them, you will always have mirror images about the y equals x line. And that's what's like I said, super important about this. Okay? So the next thing we're going to look at here is just, okay, well, visually we can determine whether or not we have inverses, okay? How do we do this algebraically? So how do we verify two functions are inverses of each other? Okay? Well, this all goes down to composition functions. So we saw that in the previous section. Okay? So basically what we're looking for is this. If we let f be 1 to 1, with domain, oops, sorry, forgot the word domain, with domain A in range B, the inverse all right, which is denoted, and that is not f to the negative 1, that is read the inverse of f, satisfies the following property, or we'll say properties. First, if you take the composite function of f and its inverse, you will get x for every x in A. And then if you just reverse the order, you get x again for every x in B. Okay? So in other words, what you have to do is you have to show, or you got to be able to put a check mark next to both of these. So you can't just check one, you have to check both. Okay? So let's go ahead and let's just do an easy example real quick. So verify that f of x equals 3x minus 2 and the inverse of x, which equals x plus 2 over 3, are inverses. Okay? So like I said, the first thing we're going to do, let's find a compositional function of f and its inverse, and it has to simplify down into x. So remember, if you want to do this, you could do this using that function calculator, the function machine that I was talking about earlier. Or you could just do it algebraically. So we're going to do ours algebraically. So what we want to find here is f of x plus 2 over 3. So I'm going to rewrite f as 3, put my big parentheses, minus 2. Then I'm going to make my substitution of x plus 2 over 3. And then simplify. Notice the 3's reduce. I get x plus 2 minus 2. When I simplify that down, I get x, so I can put a check mark. That's what I want. Step 2, let's reverse the order. All right, and let's find this compositional function. Now remember, this also has to equal x. So I'm going to write the inverse, and let's write f of x, which is 3x minus 2. Now we're going to make our substitution. So we know the inverse is going to be, I'm going to put parentheses up top in the numerator, plus 2 over 3. Now, let's make our substitution. So we get 3x minus 2. And then we simplify. 3x minus 2 plus 2 is going to be 3x over 3. The 3's reduce. So we get x again. And that's exactly what we wanted. So we can write a little statement. The functions f of x equals 3x plus 2 and the inverse of x, which equals x plus 2 over 3, are inverses. Now earlier we found that the functions f of x equals e to the x and the function g of x equals the natural log of x are inverses. We verified that visually, okay? So I'm just going to show you how to do this now using algebra. So remember, what we need to find is this. F of g of x has to equal x. Even though I didn't write the inverse of x, the idea is you still want it to simplify down into the variable x. So we have to do this first. And then second, we're going to find g of f of x. And that also has to simplify down into x. So we have f of the natural log of x, which is going to equal e to the ln of x, which is really e to the log base e of x, which simplifies down into x using our properties of logs. For part 2, we're going to do g of e to the x. Now we know this is going to be the natural log of e to the x. Using our properties of logs, we can pull out the x out front to make this x times the ln of e. And by definition, the ln of e is equal to 1, and x times 1 is x. So once again, we definitely got the outputs of x, so we know these two functions are inverses of each other. But now the big question is this. How do we find inverses? So far, I've given you inverses, or I've demonstrated where inverses do not exist, but I never showed you how to actually find an inverse. So here's how we find an inverse. So to find inverses of functions, provided they exist, here's what you're going to do. Step 1, replace f of x with the letter y. That's your first step. Step 2, swap x and y positions. Step 3, solve for y. Step 4, replace y with the inverse of x. And then 5, you always want to state your domain just to make sure everything looks nice. Okay? So earlier, we looked at this function, so we're going to find the inverse of f of x equals 3x minus, or 3x plus 2. No, I'm lying. 3x plus, or minus 2. 3x minus 2. That was the original. Okay? Now, we already know what this is. All you got to do is go back like a couple minutes in the video, and you can see where I verify that these two functions are inverses. But now we're actually going to find this. So step 1, we write y equals 3x minus 2. That's replacing f of x with y. Step 2, we swap x and y. So just literally just switch them. Just rewrite everything the way it looks. Step 3, we're going to solve this for y. So I'm just going to rewrite it first. Now I'm going to add 2 to both sides. That gives me x plus 2 equals 3y. Then I divide both sides by 3 to give me y equals x plus 2 over 3. And then step 4, we're going to replace y with the inverse of x. And I'm just going to write it from left to right. So the inverse of x equals x plus 2 over 3. And since my variable is in a numerator, I don't have to worry about any restrictions. So my domain for this is going to be negative infinity to positive infinity. And like I said, a really easy way to check yourself is just to go ahead, graph, and make sure you have that mirror image. So here's our graph. So I'm going to leave y equals x there. We get y equals 3x minus 2. And then down below that, we're going to do y equals plus 2 over 3. And notice, even though they intersect right here, you still have this mirror image of each other. Okay? So you're always going to, like I said, this y equals x line, you're always going to have mirror images of each other. And you could see how these points interact. Like this point right here, all right, I don't even know what this one is. 2.5 comma 5.5. And then if you look down here, 5.5 comma 2.5. So they're mirror images of each other. All right. Let's go. Let's do another one like this because I think this is it's kind of nice to see how this works out.